What if everything you thought you understood about a visitor from another star suddenly shifted? What if, in the span of just 3 nights, the images coming back from telescopes across the world started to tell a story that no one expected? Not even the scientists tracking it. 3. I-Atlas, the interstellar comet that astronomers have been watching closely, isn't behaving the way anyone predicted. And the newest images, captured night after night as this object passed through our solar system, are forcing us to ask questions we weren't prepared to answer. Did we just watch a comet transform in real time? Or are we witnessing something that our current understanding of space simply can't explain? For months, you've probably heard the same reassuring message: 3i Atlas is just a comet. Unusual, yes, because it came from beyond our solar system. Interesting, absolutely, because we don't get many chances to study objects from interstellar space, but ultimately it's natural. It's ice and rock and dust, following the same rules that govern every other comet we've ever seen. And for a while, that explanation seemed to fit. But then the new images arrived. Images taken over consecutive nights, processed by multiple observatories, analysed by teams around the world, and suddenly the story isn't so simple anymore. The glow around the comet's core seems to shift. The tails stretching away from the sun appear to change shape, split, and realign in ways that spark debate. And in some of the most detailed frames, features appear that don't look like anything we've seen before. Features that some scientists describe as natural phenomena, while others stop and ask a more uncomfortable question: what if we're looking at something we don't have a category for yet? This isn't about jumping to wild conclusions. It's about looking at the evidence with open eyes and asking the questions that need to be asked. Because when you line up these images side by side, frame by frame, you start to see changes that happen too fast, or in ways that seem too structured, too deliberate. You see patterns that make you pause. And whether those patterns are the result of natural forces we don't fully understand, or something else entirely, the fact remains: these images are changing the conversation. They're forcing astronomers to rethink their models. They're giving fuel to researchers who have long suggested that not every interstellar object is what it seems. And they're leaving all of us, scientists and curious minds alike, staring at the same screens, asking the same question: what are we really looking at? You and I, we're not astrophysicists. We don't have access to the world's most powerful telescopes or the complex software used to model comet behaviour. But we have something just as valuable: the ability to look at the same images the experts are looking at and ask our own questions. We have the ability to follow the data, to listen to the debate, and to think critically about what we're being told. And right now, what we're being told doesn't quite add up. On one side, you have NASA and mainstream astronomers saying this is a comet, plain and simple. On the other side, you have voices like Loeb, a Harvard astrophysicist who has built a career on asking uncomfortable questions, pointing to these same images and saying, wait, look closer. There's something here that doesn't fit the standard model. The truth is, we're standing at a crossroads. Either these images confirm what we already believed, that 3i Atlas is a fascinating but ultimately natural comet, or they reveal something deeper, something stranger, something that challenges the assumptions we've held for decades. And the only way to find out which path we're on is to do the work, to go through these images carefully, to understand what mainstream science is saying, to weigh the alternative theories, and to arrive at our own conclusions based on the evidence. Not on hype, not on fear, not on the desire to believe one story over another, but on the cold, clear data that's sitting right in front of us. In the space of just a few nights, 3i Atlas went from being a distant curiosity to a central mystery. It went from a headline that most people scrolled past to a question that won't let go. And whether you're someone who believes we're alone in the universe, or someone who's always suspected we're not, these images matter. They matter because they're real. They matter because they're changing the way scientists talk about interstellar objects. And they matter because for the first time in a long time we have a chance to be part of the investigation. Not as passive observers, but as active participants in a global conversation about what's out there and what it means for us down here. So stay with me, because in the next minutes we're going to walk through these images together. We're going to look at what they show, what they don't show, and what they might mean. We're going to hear from the scientists who say this is all perfectly normal, and from the ones who say we're missing something critical. We're going to explore the debates, the theories, and the hard evidence that's driving this entire conversation. And by the end, you'll have a clearer picture of what's really happening with 3i Atlas, and why these images might just change everything we thought we knew. If you want more people to see what's hiding in these frames, hit the like button right now. Tell me in the comments where in the world you're watching from, because this mystery doesn't belong to one country, one institution, or one scientist. It belongs to all of us. And the more of us who pay attention, who ask questions, and who demand real answers, the closer we get to the truth. So let's get started. Let's look at what these images actually show, and why they're causing so much debate in the first place. Let's start with what we can see. Not what we think we see, or what we want to see, but what the images themselves reveal when we look at them objectively. Because before we dive into theories and debates, we need to establish a baseline. We need to understand what astronomers on all sides of this conversation agree on, and here's what they agree on. 3i Atlas is active, very active, more active than many expected an interstellar comet to be, and that activity is captured in these new images in stunning detail. When you first look at the images, the most obvious feature is the coma. That's the glowing cloud of gas and dust that surrounds the comet's nucleus, the solid core at the centre. In the case of 3i Atlas, the coma is bright, unusually bright for an object that's travelled across light years of freezing space. This brightness tells us that the comet is releasing material, vaporizing ice, shedding dust, reacting to the heat and radiation from our sun. And that's normal. That's what comets do. As they approach the sun, the ice on their surface heats up, turns to gas, and drags dust particles along with it. The result is this glowing halo that can stretch for thousands of miles around the nucleus. So far, so expected. But then you notice the tails. Every comet has a tail, or usually two, a dust tail and an ion tail. The dust tail is made of tiny particles pushed away by sunlight, and it tends to curve gently along the comet's orbit. The ion tail is made of charged particles blown back by the solar wind, and it points directly away from the sun. Straight and narrow. In the images of 3i Atlas, both types of tails are visible, and they're not subtle. The ion tail in particular is sharp and well-defined, stretching out in a long, thin line that tells you this comet is reacting strongly to the solar wind. That's still within the realm of normal comet behaviour, but here's where it gets interesting. In some of the images, the tails seem to split. They branch off, or new structures appear alongside the main tail, and astronomers have different explanations for why this happens. Some say it's a sign of multiple outbursts. Comets don't release gas evenly. They have jets, active regions on their surface where material erupts in bursts. If a comet has several of these jets firing at different times, you can get complex tail structures. You can get what looks like multiple tails, or tails that change shape from one night to the next. That's a known phenomenon. It's been observed in other comets. So when mainstream scientists look at 3i Atlas and see these branching tails, they say, yes, that's unusual, but it's not unprecedented. It's just a very active comet with multiple jets. Then there's the shape. In some of the images, especially the ones taken with longer exposure times, 3i Atlas appears elongated. It's not a perfect round glow. It's stretched out, almost like a line or a streak. And again, there are straightforward explanations for this. Motion blur, for one. The comet is moving fast, very fast, and if the telescope tracks it over several minutes while capturing light, you can get a smeared image. The comet's light stretches across the sensor, creating that elongated appearance. Some analysts also suggest that the comet's nucleus might be rotating, or that the coma itself is asymmetric, with more material on one side than the other. All of these are possibilities. All of them fit within the natural comet model. But here's the thing. Not everyone is satisfied with those explanations. Some observers look at the same images and see something more. They see structures that seem too straight, too organized to be the result of random gas jets or motion blur. They see patterns in the glow that suggest alignment, symmetry, or coordination. And they start to wonder if there's more to this story than we're being told. That's the tension running through this entire conversation. The images themselves are objective. They're just light captured by sensors. But the interpretation of those images is where the divide begins. Imagine you're looking at a snowball flying through the air, shedding flakes as it goes. Now imagine that snowball is moving at tens of thousands of miles per hour, and it's been travelling through the freezing vacuum of space for millions of years. When it finally gets close to a star, our sun, it starts to warm up, and all that frozen material begins to react. Gas jets erupt from the surface. dust streams out behind it, the solar wind catches the charged particles and sweeps them into a tail that can stretch for millions of miles. That's the basic picture. That's what astronomers see when they look at 3i Atlas, and for most of them, that picture is enough. It's beautiful, it's dynamic, and it's perfectly consistent with what we know about comets. But there are details in these images that keep some researchers up at night, details that aren't easy to explain away with a simple model, and whether those details point to something extraordinary, or whether they're just the limits of our current understanding, the fact is that they're there, they're in the data, they're in the images, and they're the reason this conversation is happening at all, because if we're going to claim that we understand what 3i Atlas is, we need to be able to explain everything we see, not just the parts that fit our expectations. And right now, there are parts of these images that challenge those expectations, parts that make even the most skeptical scientist pause and take a second look. So that's the baseline. That's what the images show. A bright, active, complex comet with multiple tails, a dynamic coma, and features that change over time. Features that most scientists say are natural, but that some believe deserve a deeper investigation. And now that we've established what we're looking at, we can move into the harder question: who's right? The mainstream view that says this is all perfectly normal, or the alternative voices saying we need to consider possibilities we've been too quick to dismiss. Here's where the story splits. On one side, you have the institutional view. NASA, the European Space Agency, and the vast majority of professional astronomers all agree. 3i Atlas is a comet. It's an interstellar comet, which makes it scientifically valuable and worthy of intense study, but it's still a comet. It's made of ice and rock. It's following a predictable orbit. It's behaving in ways that, while complex, are entirely consistent with known comet physics. There's no need to invoke exotic explanations. There's no reason to assume this object is anything other than a natural traveller from another star system. And for these scientists, the new images, as intriguing as they are, don't change that fundamental assessment. They point to decades of comet research. They point to missions like Rosetta, which spent years studying a comet up close and revealed just how complicated these objects can be. They point to ground-based observations of other comets that showed similar tail structures, similar outbursts, similar variability. And they say, look, we've seen this before, maybe not with an interstellar comet, but with comets in general. The physics is the same, the processes are the same. The only thing different about 3i Atlas is where it came from. And that's a powerful argument. It's grounded in evidence, it's grounded in experience, and it's the position held by the overwhelming majority of the scientific community. But then there's the other side, and on that side you have voices like Avi Loeb. Loeb isn't some fringe figure, he's a Harvard astrophysicist. He's published hundreds of papers, he's chaired major scientific committees, he's respected in his field even by those who disagree with him, and over the past few years Loeb has become the most prominent advocate for the idea that we need to seriously consider the possibility that some interstellar objects might not be natural, that they might be technological, that they might be, in the simplest terms, alien artifacts. Now, before you dismiss that as science fiction, understand that Loeb isn't saying he has proof. He's not claiming that 3i Atlas is definitely a spacecraft. What he's saying is that we have a responsibility to investigate, to look at the evidence without preconceptions, to consider all possibilities, even uncomfortable ones, and to follow the data wherever it leads. And when Loeb looks at the new images of 3i Atlas, he sees things that give him pause. He sees features that don't quite fit the simple comet model. He sees structures that to him suggest the possibility of something more deliberate, more organised, more engineered. Loeb has pointed to the unusual acceleration that some interstellar objects exhibit. He's talked about shapes and reflectivity patterns that don't match what we expect from natural bodies. And now, with 3i Atlas, he's highlighting what he describes as linear features, straight lines in processed images that he suggests could be tracks or trails of smaller objects moving alongside the comet. He's careful to say that this is a hypothesis. He's clear that it's not proven. But he's also clear that, in his view, the evidence is strong enough to warrant serious investigation. And that's where the conflict lies, because the mainstream scientists don't see what Loeb sees, or more accurately, they see the same features, but interpret them differently. Where Loeb sees potential signs of technology, they see processing artifacts, image smearing, or natural debris. Where Loeb sees anomalies that demand explanation, they see expected variability in a highly active comet, and so you have this divide. not a divide between science and pseudoscience, but a divide within science itself. A divide between those who think the current models are sufficient and those who think we're missing something important. And here's the thing, both sides could be right in a way. It's possible that 3I Atlas is a completely natural comet, and that Loeb and others like him are reading too much into ambiguous data. It's also possible that the mainstream view is missing something, that there are real anomalies in the data that deserve deeper investigation. Science is supposed to be a process of testing ideas against evidence, of remaining open to new possibilities while demanding rigorous proof. And right now, that process is playing out in real time, with 3I Atlas as the test case. For you, the viewer, this debate matters because it's not just about one comet. It's about how we approach the unknown. It's about whether we're willing to ask uncomfortable questions, even when those questions make us look foolish or naive. It's about whether we trust the institutions that have been studying space for decades, or whether we listen to the voices on the margins who say, well, wait, let's look at this more carefully. And the answer isn't simple. It's not about choosing a side and sticking to it no matter what. It's about staying curious, staying critical, and staying open to the possibility that the universe might surprise us. So who's right? The institutions that see a strange but natural comet, or the outsider voice asking if we should also consider a more radical possibility? The honest answer is, we don't know yet. We don't have enough data to say definitively. What we have are images, measurements, theories, and debates. And what we need is more time, more observations, and more transparency. We need scientists on both sides to keep talking, to keep testing their ideas, and to keep sharing their findings with the rest of us. Because in the end, the truth will come out. It always does. And when it does, we'll look back at these images, at this moment, and we'll understand what we were really seeing all along. But until then, the debate continues, and that's exactly where we need to turn our attention next, to the details of these images night by night, and what they reveal about how 3I Atlas is changing over time. There's something deeply unsettling about watching an object change when you expected it to stay the same, and that's exactly what happened with 3I Atlas over the course of several nights. Multiple observatories, from professional facilities to dedicated amateur astronomers, pointed their instruments at this interstellar visitor and captured image after image. And when those images were placed in sequence side by side, something became clear. This wasn't a static object. It was evolving, shifting, transforming in ways that were subtle at first, but impossible to ignore once you knew what to look for. Let's talk about what it means to observe something over time. When you take a single image of a comet, you get a snapshot, a frozen moment. It's beautiful, it's informative, but it's limited. You see where the comet is, how bright it is, what its general structure looks like. But you don't see the story. You don't see the motion, the change, the dynamics that define what this object really is. To get that, you need a series of images. You need to come back night after night, capturing the same object from the same perspective, and then you need to compare those frames carefully. And that's what researchers did with 3I Atlas. They built a time series, a visual record of how this comet behaved as it moved deeper into our solar system. What they found was fascinating. In the first set of images taken on one night, the comet appeared roughly symmetrical. The bright glow around the nucleus was centered, with a gradual fade-off toward the edges. The tail stretched out behind the comet, pointing away from the sun, just as expected. Nothing unusual. But then, the next night, something shifted. The coma looked slightly elongated, as if more material was being released from one side than the other. The tail seemed to thicken in some areas and thin in others. And in the processed versions of the images, where contrast and brightness were enhanced to bring out faint features, hints of additional structure began to appear. Faint lines, secondary tails, patterns that weren't visible in the raw frames. By the third night, the changes were even more pronounced. The tail had split into multiple branches. The coma showed asymmetries that suggested active jets firing from specific points on the nucleus. And in some of the highest resolution images, observers noted what appeared to be discrete clumps of material within the coma, moving outward from the center. To mainstream astronomers, this was all expected behavior. Comets are dynamic objects. They rotate, they outgas unevenly, they respond to the solar wind in complex ways. A comet that's active enough can easily produce multiple tails, can show asymmetries, can release chunks of ice or dust that glow as they move away from the nucleus. So when they looked at the night-by-night progression, they saw a comet doing what comets do. Nothing more. But for others, the progression told a different story. They looked at the same sequence of images and saw patterns that seemed too organized to be random. They saw structures that appeared and then disappeared, as if something was moving through the coma in a controlled way. They saw alignments that suggested coordination, not chaos, and they began to ask, what if we're watching more than just gas and dust? What if there's something else in these images, something small and hard to see, that's influencing the way the coma behaves? Now let's be clear, these are speculative questions. They're not based on definitive proof. They're based on observations that are open to multiple interpretations, and that's important to remember because it's easy to get carried away. It's easy to see a pattern and assume it means something when it might just be a coincidence, an artifact, or a natural process we don't fully understand yet. But it's also important not to dismiss these questions out of hand, because sometimes the things that seem too strange to be true are exactly the things that push science forward. One of the most striking aspects of the time series images is how quickly things change. We're not talking about weeks or months. We're talking about changes that happen from one night to the next. Changes that, in some cases, happen within hours. The coma brightens, then dims. The tail shifts direction, then realigns. Structures appear in one frame and vanish in the next. And while astronomers can explain many of these changes with existing models, rotation, outbursts, variable solar wind, there are moments where the explanations feel like they're being stretched to fit the data rather than the data fitting naturally into the explanations. Imagine you're watching security camera footage of a parking lot. Most of the time you see cars moving predictably. They park, they leave, they follow the painted lines. But then you notice something odd. A car that seems to move sideways without turning its wheels. A shadow that doesn't match the position of the light source. A pattern that repeats too precisely to be random. You might shrug it off as a glitch in the camera, a trick of the light, a misunderstanding of the angle. But you might also lean closer to the screen and think, wait, something's not right here. That's the feeling some researchers get when they study the night-by-night progression of 3I Atlas. Not certainty that something strange is happening, but a nagging sense that the standard explanations aren't quite capturing the full picture. And then there's the role of image processing. Raw images from telescopes are often dim, noisy, and cluttered with background stars and cosmic rays. To bring out the faint details of a comet, astronomers use software to stack multiple frames, subtract background noise, and enhance contrast. This is a standard technique. It's how we see structures that would otherwise be invisible, but it's also a technique that can introduce artifacts. It can create lines, edges, and patterns that aren't really there, that are just byproducts of the processing algorithms. So when someone points to a faint linear feature in a processed image and says, look, that's anomalous, the first question has to be, is that a real feature, or is it an artifact? Most of the time, with careful analysis, you can tell the difference. You can check multiple frames, try different processing methods, compare with other observatories' data. And if the feature is real, it will show up consistently. If it's an artifact, it will change or disappear when you adjust the processing. The problem is that not all features are that clear-cut. Some sit right on the edge of detectability. Some appear in some frames and not in others. Some look real in one processing pipeline and fake in another, and those are the features that drive the debate. Those are the ones that Loeb and others point to and say, we need to investigate this more carefully, while mainstream scientists say, that's just noise, that's just the limits of our instruments. So what do we take away from this night-by-night progression? We take away the fact that 3I Atlas is not a simple object. It's active, it's variable, it's responsive to its environment. We take away the fact that the images, when viewed in sequence, reveal a level of complexity that wasn't obvious from a single snapshot. And we take away the fact that this complexity is open to interpretation. Some see it as the natural behavior of a highly active comet. Others see it as a sign that something more is going on, something that deserves closer scrutiny. And the only way to resolve that difference is to keep watching, keep imaging, and keep asking questions. Which brings us to one of the most controversial claims to come out of this entire investigation. The idea that there are thin, straight lines in these images that might represent tracks of separate objects moving alongside the comet. Lines that some call the companions. This is where the conversation gets uncomfortable. Because up until now, we've been talking about features that, while debated, are at least within the realm of recognized comet behavior. Tails, comas, outbursts, these are things we expect to see. But now we're going to talk about something else. Something that, if real, doesn't fit neatly into any existing category. We're going to talk about the straight lines, the tracks. The features that Avi Loeb and a few other researchers have identified in the processed images of 3I Atlas and called possible evidence of companions, smaller objects moving alongside the comet, leaving faint trails in the data. Let's start with what these features actually look like. In the raw images, you don't see them. The raw frames show the comet, the coma, the tails, and a lot of background stars, but when you take multiple images, stack them together, and apply contrast enhancement, certain faint structures start to emerge. And among those structures, in some of the processed frames, there are thin, nearly straight lines. They extend outward from the general region of the comet. They're not curved like a tail. They're not diffuse like the coma. They're narrow, well-defined, and in some cases, almost geometric in their appearance. And that's what caught Loeb's attention. In his analysis, Loeb suggests that these lines could be the paths of separate objects, not chunks of ice or dust randomly ejected from the comet, but discrete bodies moving on their own trajectories. He raises the possibility, carefully as a hypothesis, that these could be fragments that split off from the comet, or, more provocatively, that they could be small devices, probes, or artifacts that were released as 3I Atlas passed through our system. He's clear that this is speculative. He's clear that it's not proven. But he's also clear that, in his view, the lines are there. They're real, and they deserve investigation. Now, before we go any further, let's talk about why this claim is so controversial. Because it's not just that Loeb is suggesting the possibility of technology, it's that he's doing so based on features that are incredibly difficult to verify. These lines are faint, they're only visible in heavily processed images, they don't show up in every frame, and they're exactly the kind of feature that can be created by artifacts, by stacking misalignments, by cosmic ray hits, by background objects that happen to line up in just the right way. So when mainstream astronomers hear Loeb's claim, their immediate response is skepticism. Not because they're closed-minded, but because they've seen this kind of thing before. They've seen how processing can create false signals, and they know that extraordinary claims require extraordinary evidence. So what's the evidence? Loeb points to the consistency of the lines in certain frames. He points to their orientation, which he says is not random but seems to follow specific directions relative to the comet's motion. He points to their length and straightness, which he argues is difficult to explain if they're just background objects or artifacts. And he points to the timing. These lines appear in images taken over consecutive nights, which suggests they're associated with the comet itself, not with something stationary in the background. But here's the counter-argument. Other astronomers have looked at the same data and reached different conclusions. They point out that when you stack images of a moving object, especially one that's moving as fast as 3I Atlas, you can easily create streaks and lines that aren't real. They point out that cosmic rays, high-energy particles from space that hit the camera sensor, can leave long, straight trails that look remarkably similar to what Loeb describes. They point out that background stars, if the telescope tracking isn't perfect, can also smear into lines. And they point out that the lines don't show up in independent observations from other telescopes, which suggests they might be specific to the processing methods used in the images Loeb analysed. So who's right? That's the question we keep coming back to. And the answer is, we need better data. We need more telescopes, with higher resolution, capturing more frames over longer periods. We need independent teams to analyse the same data using different processing techniques and see if they get the same results. We need transparency, with raw data made available so that anyone can check the claims. And we need time. Because right now we're in the middle of the investigation. We're not at the end. We don't have the final answer. What we have is a claim, a counterclaim, and a lot of uncertainty. But let's talk about what it would mean if the lines are real. If they're not artifacts, not cosmic rays, not background objects, but actual tracks of something moving through the region around 3I Atlas. The most conservative interpretation is that they're fragments, pieces of the comet that broke off due to thermal stress, rotation, or outgassing pressure. Comets do fragment. We've seen it happen, and when a fragment splits off, it follows its own orbit, slowly drifting away from the parent body. If that fragment is glowing, either because it's still outgassing or because it's reflecting sunlight, it could leave a faint trail in long exposure images, So the lines could be natural debris. That's the explanation that most scientists would favour. But then there's the other interpretation, the one that Loeb is willing to entertain, even if it makes him a target of criticism. What if the lines are not fragments, but something else? What if they're small, controlled objects? What if 3I Atlas, in addition to being a comet, is also carrying something? And what if that something was released, intentionally or not, as it passed through our solar system? This is the interpretation that makes headlines. This is the interpretation that gets people excited, or angry, or dismissive. Because it's not just about science anymore. It's about philosophy. It's about our place in the universe. It's about whether we're alone or not. And those are questions that touch something deeper than data and analysis. Here's the thing, though. Asking the question doesn't mean you have the answer. Loeb isn't saying he knows these are alien probes. He's saying we should investigate the possibility. And there's a difference. A big difference. Science progresses by testing ideas, even wild ideas, and seeing if they hold up under scrutiny. If the idea of companions is wrong, then better data and analysis will show that. If it's right, or if there's some truth to it, then we need to know. Because if there's even a chance that an interstellar object is carrying something technological, then we have a responsibility to look. To really look. Not to dismiss it because it sounds too strange, but to examine it with the same rigour we'd apply to any other scientific claim. And that's where we are right now. We're in the uncomfortable middle ground where the data is ambiguous, the interpretations are divided, and the stakes are higher than anyone wants to admit. The lines are there, or they're not. They're real, or they're artifacts. They're natural, or they're something else. And the only way to find out is to keep pushing, keep questioning, and keep demanding better evidence, which means we need to turn to the mainstream response. We need to hear from the scientists who have looked at these same claims and said, no, this is not evidence of anything anomalous. This is normal comet behaviour, and here's why. Every bold claim needs a counterbalance. Every extraordinary hypothesis needs skeptics who will poke holes, test assumptions, and demand proof. And when it comes to the claims about 3I Atlas, about unusual structures, sideways lines, and possible companions, mainstream science has been more than willing to push back. Not because scientists are closed-minded, but because they understand how easy it is to see patterns that aren't there, how easy it is to misinterpret data, and how important it is to separate real signals from noise. Let's start with the most fundamental point. Comets are messy. They're not solid, uniform objects. They're conglomerates of ice, dust, rock, and organic material loosely held together by gravity. When they get close to the sun, they don't melt evenly. Different parts of the surface heat up at different rates. Some areas release gas violently, creating jets, other areas stay dormant. And as the comet rotates, these jets turn on and off, creating a complex, ever-changing pattern of outgassing. This is well documented. Missions like Rosetta, which orbited and landed on a comet, showed us just how chaotic these objects are up close. So when astronomers look at 3I Atlas and see variability, asymmetry, and multiple tails, their first thought is, this is what comets do. The splitting tails, explained by multiple jets firing at different times. The elongated coma, explained by rotation and uneven outgassing. The changes from night to night, explained by the comet's spin, its changing distance from the sun, and variations in the solar wind. All of these explanations are grounded in established physics. They don't require any new assumptions. They don't require any exotic processes. They just require understanding that comets are dynamic, active objects that respond to their environment in complex ways. Now let's talk about the straight lines, the so-called tracks of companions. Mainstream astronomers have several explanations for these features, and none of them involve separate objects moving alongside the comet. First, there's the processing artifact explanation. When you stack multiple images of a moving object, any misalignment in the stacking process can create streaks. If the telescope tracking isn't perfectly synchronized with the comet's motion, background stars will smear into lines. If the frames aren't aligned to subpixel accuracy, the comet itself can leave trails, and if you apply aggressive contrast enhancement, these subtle misalignments become much more visible, creating the appearance of straight lines where none exist in the original data. Second, there are cosmic rays. These are high-energy particles from space, mostly protons and atomic nuclei, that constantly bombard Earth and anything in space. When a cosmic ray hits a camera sensor, it deposits energy, creating a bright streak across the image. These streaks can be long, perfectly straight, and remarkably bright. And if you're stacking multiple images without proper cosmic ray rejection algorithms, these streaks can accumulate and create patterns that look like trails. Professional astronomers are very familiar with this problem, and they have standard techniques for filtering out cosmic rays. But if those techniques aren't applied, or if they're applied imperfectly, cosmic ray hits can easily be mistaken for real astronomical features. Third, there's the background star explanation. The region of sky where 3i Atlas appears is not empty. There are thousands of faint stars in the background, and if the telescope's tracking is even slightly off, if it drifts by a fraction of an arc-second over the course of a long exposure, those stars will trail. They'll leave short straight lines in the image, and if several stars happen to line up in a particular direction, those lines can create the appearance of a coordinated pattern. To an untrained eye, or to someone who wants to see something unusual, these star trails can look like evidence of separate objects moving through the field, but to an experienced astronomer, they're just a well-known artifact of imperfect tracking. Multiple independent astronomers have analysed the same images that Loeb highlighted, and many have concluded that the lines are most likely artifacts. They've shown how changing the processing parameters makes the lines disappear or shift position. They've shown how similar lines appear in images of other comets and asteroids, where there's no reason to suspect anything anomalous. And they've shown how the lines don't correlate with any physical features of the comet itself. They're not aligned with the tail, they don't follow the motion of the coma, and they don't appear consistently in every observation. All of this points to the conclusion that the lines are not real features of 3i Atlas, but rather artifacts of the imaging and processing. Then there's the question of the comet's unusual acceleration. Some researchers have noted that 3i Atlas, like another interstellar visitor before it, seems to be moving slightly faster than expected based on gravitational forces alone. This is often cited as evidence of something unusual, something that might suggest non-gravitational forces at work. But again, mainstream science has an explanation: outgassing. When a comet releases gas, it's not a passive process. The gas jets outward, and by Newton's third law, the comet experiences a tiny push in the opposite direction. This is called the rocket effect, and it's a well-known phenomenon. Over time, these tiny pushes can add up, changing the comet's trajectory in measurable ways. So when astronomers see a small, unexplained acceleration in 3i Atlas, their immediate thought is outgassing. Not alien propulsion, not mysterious technology, just gas venting from the surface. And here's the bigger point. Science doesn't work by assuming the most exciting explanation is true. Science works by testing the simplest explanation first, and only moving to more complex or exotic explanations if the simple ones fail. This is Occam's razor. When you have multiple explanations that fit the data, you start with the one that makes the fewest new assumptions. In the case of 3i Atlas, the simplest explanation is that it's a comet. A strange comet, an interstellar comet. A comet that challenges our models in some ways, but still a comet. And until there's clear, unambiguous evidence that this explanation is wrong, that's the position that most scientists are going to hold. Does that mean they're right? Not necessarily. History is full of examples where the mainstream view was wrong, where outsiders who asked uncomfortable questions turned out to be correct. But history is also full of examples where exciting claims turned out to be misunderstandings, artifacts, or wishful thinking. So the smart approach is to stay skeptical, to demand rigorous evidence, and to remain open to changing your mind if better data comes along. And that's exactly what mainstream astronomers are doing. They're not dismissing the possibility that 3i Atlas is unusual. They're just saying that, based on the current evidence, there's no reason to think it's anything other than a natural object. So where does that leave us? It leaves us with two competing narratives. On one side, you have the majority of astronomers saying this is a comet, the anomalies are explained, and there's no mystery here. On the other side, you have a small group of researchers saying the anomalies are real, the explanations are insufficient, and we need to investigate further. And in the middle, you have the rest of us, trying to make sense of the data and figure out who to trust. The answer, as always, is to trust the process, trust the scientific method, Trust that better observations, better analysis, and honest debate will eventually lead us to the truth. And in the meantime, let's look at what these images, anomalies or not, actually tell us about 3I Atlas. Because even if this turns out to be just a comet, it's a comet that's changing the way we think about interstellar visitors. Step back for a moment. Forget the debates, the theories, the controversy. Forget whether Loeb is right or wrong, whether the lines are real or artifacts, whether there are companions or just cosmic rays. Forget all of that and focus on what we know for certain. These images are remarkable. They're showing us things we've never seen before, at least not with this level of detail and clarity. And regardless of how you interpret them, they're changing the story of 3I Atlas. They're transforming this object from a distant curiosity into a living, breathing mystery that's unfolding in real time. Let's start with what makes these images genuinely new and important. Before they were captured, our understanding of 3I Atlas was limited to basic observations. We knew its trajectory. We knew it was an interstellar comet. We knew it was approaching the sun and starting to brighten. But we didn't have a detailed picture of what was happening to it. We didn't know how active it would become. We didn't know what its coma and tails would look like. We didn't know whether it would behave like comets from our own solar system, or whether being born in another star's neighborhood would make it fundamentally different. Now we know. These images give us a window into the comet's behavior at a level of detail that was impossible before. We can see the structure of the coma, we can track the evolution of the tails, we can watch as material is released from the nucleus and swept back by the solar wind. We can measure the brightness, the color, the distribution of light across the comet's surface. And all of that is scientifically valuable. It's data that astronomers can use to refine their models of comet physics. It's data that helps us understand how interstellar objects react to our sun. It's data that, in the long run, will tell us more about the conditions in other star systems, the chemistry of interstellar space, and the processes that create and shape these icy wanderers. One of the most striking things the images reveal is just how active 3I Atlas is. Astronomers expected some activity. All comets become active as they approach the sun, but the intensity caught many by surprise. The coma is large and bright. The tails are long and well-defined. There are clear signs of multiple outbursts, multiple jets, and ongoing material loss. This tells us that the comet's composition is rich in volatile materials, substances that evaporate easily when heated, and that in turn tells us something about where it came from. It suggests that 3I Atlas formed in a cold, distant region of its home star system, far enough out that these volatiles could freeze and be preserved for millions or billions of years. The images also show us the comet's response to the solar wind. The ion tail, that long straight tail pointing directly away from the sun, is a direct result of the solar wind interacting with the gas released by the comet. Charged particles in the gas are caught by the magnetic field, embedded in the solar wind, and dragged outward at high speed. The sharpness and brightness of 3I Atlas's ion tail tell us that the comet is releasing a lot of ionized gas, and that the solar wind in this region of space is strong and well organized. This is the kind of detail that helps astronomers understand not just the comet, but the environment it's traveling through. And then there's the variability. The fact that the comet looks different from one night to the next is important. It tells us that the comet is not a passive object being pushed around by external forces. It's an active participant in its own evolution. It's rotating, it's venting gas unevenly, it's responding to changes in sunlight and solar wind. And all of that variability gives astronomers clues about the comet's internal structure. Is it a single solid body, or a loose pile of rubble held together by weak gravity? Does it have a fast rotation, or a slow one? Are the jets coming from a few large vents, or from many small cracks? These are questions that can be answered, at least partially, by carefully studying how the comet changes over time. But here's where it gets interesting. Even if we accept the mainstream view that 3I Atlas is a natural comet, nothing more, the images still change everything in a very real sense, because they show us that interstellar comets are not just rare curiosities, they're dynamic, complex, scientifically rich objects that can teach us about processes we can't study anywhere else. They're windows into other star systems, they're samples of alien environments, delivered to our doorstep free of charge. And the more we learn about them, the more we realize how much we still don't understand about our own solar system, let alone the galaxy beyond. Now let's talk about the other side, the speculative side. Because for some people, these images don't just refine the natural comet model, they challenge it. They open the door to possibilities that most scientists are reluctant to consider, and whether those possibilities are real or not, they're part of the story now, they're part of the conversation, and they matter because they reflect something deeper, our collective desire to know if we're alone in the universe. When Avi Loeb looks at these images and sees potential signs of technology, he's not just talking about data. He's talking about hope. He's talking about the idea that the universe might be full of civilizations, full of intelligence, full of artifacts waiting to be discovered. And he's saying that we owe it to ourselves to look, to really look, not to dismiss every strange observation as noise or error, but to investigate with the same openness and rigor we'd apply to any other scientific question. And that's a powerful message. It's a message that resonates with a lot of people, especially those who feel like mainstream science is too cautious, too conservative, too quick to explain away the weird and the wonderful. But here's the tension. If you're too quick to see aliens in every anomaly, you lose credibility. You stop being a scientist and start being a believer. And belief, in the absence of evidence, is not science, it's faith. So the challenge is to walk the line, to stay curious without being gullible, to ask bold questions without jumping to bold conclusions, to look at these images of 3i Atlas and say, yes, there are things here I don't fully understand, yes, some of the features are strange, but no, that doesn't mean I know what they are. It means I need more data. It means I need to keep investigating. And that's the real takeaway from these images. They don't give us final answers. They give us better questions. They show us that 3i Atlas is more complex, more active, more interesting than anyone expected. They show us that our models of comets, while good, are not perfect. They show us that the universe still has the power to surprise us. And they show us that we're living in a moment where, for the first time in history, we have the tools to study interstellar objects in real time as they pass through our neighborhood. That's extraordinary. That's genuinely new. And that's what these images represent, no matter how you interpret them. So yes, the images change everything. They change our understanding of 3i Atlas from a simple object into a complex one. They change the debate from, is it interesting, to what does it mean? And they change the stakes, because now we're not just talking about one comet. We're talking about a whole class of objects that we're only beginning to understand. Interstellar visitors, messengers from other star systems, and every image, every observation, every data point brings us closer to understanding what they are, where they come from, and what they can teach us. Which brings us to the future, to what happens next, to the observations that are still coming, and the discoveries that are still waiting to be made. The story of 3i Atlas is not over, not even close. We're in the middle of the investigation, not at the end. And in many ways, the most important observations are still to come. Because as this interstellar comet continues its journey through our solar system, it's going to get brighter, more active, and easier to study. And astronomers around the world are preparing to take full advantage of that opportunity. Right now, 3i Atlas is approaching perihelion, the point in its orbit where it passes closest to the Sun, and as it does, the heat and radiation from the Sun are going to intensify. The comet's surface is going to warm up even more, the rate of outgassing is going to increase, the coma is going to grow larger and brighter, the tails are going to stretch out even farther, and all of that activity is going to make the comet easier to observe, even for smaller telescopes. This is the window that astronomers have been waiting for. The window where 3i Atlas reveals its secrets most clearly. Multiple observatories are already lined up to watch. Large ground-based telescopes are dedicating time to capturing high-resolution images and spectra. Space telescopes, which can observe in wavelengths that don't penetrate Earth's atmosphere, are turning their instruments toward the comet. And amateur astronomers, who often contribute valuable data in these situations, are tracking it night after night, building up long time series observations that professional facilities might not have the time to capture. It's a coordinated global effort, and the data that comes out of it is going to be the best we've ever had for an interstellar comet. So what are astronomers looking for? First, they want better images, higher resolution, longer exposure times, more wavelengths. They want to map the coma in detail, to see exactly where the gas and dust are coming from. They want to track the tails over time, to measure their motion, their structure, their changes. They want to look for fragments, for pieces that might have broken off the nucleus, and they want to search for faint features that might be hiding in the noise, features that could either confirm or rule out some of the more controversial claims about this object. Second, they want spectra. Spectroscopy is the technique of splitting light into its component colours and measuring the intensity at each wavelength. Different molecules emit and absorb light at specific wavelengths, so by taking a spectrum of the comet, astronomers can figure out what it's made of. They can detect water, carbon dioxide, methane, ammonia, and a whole host of other chemicals. And by comparing the composition of 3I Atlas to comets from our own solar system, they can learn about the similarities and differences between different stellar environments. They can test whether the chemistry of interstellar space is fundamentally the same as the chemistry here at home, or whether there are surprises waiting. Third, they want precise trajectory measurements. The more accurately we can track the comet's position over time, the better we can model its orbit. And the better we model its orbit, the more clearly we can see any deviations from a purely gravitational path. If there are non-gravitational forces at work, whether that's outgassing, solar radiation pressure, or anything else, those forces will show up as tiny shifts in the comet's motion. And by measuring those shifts, astronomers can infer properties of the comet that are hard to see directly, like its mass, its rotation rate, and the strength of its outgassing jets. Fourth, and perhaps most importantly, they want to test the claims. The claims about unusual acceleration, the claims about straight-lined features, the claims about possible companions. Every one of these claims can be tested with better data. If the lines are real, they'll show up in independent observations. If they're artifacts, they'll disappear when you use different instruments or different processing techniques. If there are separate objects moving alongside the comet, they'll leave a consistent signature across multiple nights and multiple telescopes. And if there's nothing there, that will become clear too. Science is not about proving what you believe, it's about testing what you think might be true and seeing if it holds up. And that's exactly what's going to happen with 3I Atlas over the next weeks and months. Now, let's talk about what the outcomes might be. There are really three possibilities. The first is that everything resolves neatly into the natural comet model. The anomalies turn out to be artifacts or misinterpretations. The acceleration is fully explained by outgassing. The structure and variability are consistent with known comet physics. And 3I Atlas, while fascinating, is ultimately just a comet. That would be the most likely outcome based on current evidence, and it would still be a win for science because we'd have learned a tremendous amount about interstellar comets, and we'd have refined our models and techniques for studying them. The second possibility is that there are real surprises in the data, but they're natural surprises. Maybe 3I Atlas has a composition we didn't expect. Maybe it's rotating in an unusual way. Maybe it's undergoing processes that we haven't seen in other comets. These would be anomalies, yes, but anomalies that expand our understanding of natural phenomena, not evidence of technology. This outcome would be scientifically exciting. It would give astronomers new puzzles to solve, new models to build, new papers to write, and it would remind us that the universe is more complex and more varied than we often give it credit for. The third possibility is the one that keeps some people up at night and that others dismiss as fantasy. It's the possibility that there really is something anomalous about 3I Atlas, something that can't be explained by natural processes alone, that the unusual acceleration is not just outgassing, that the straight lines are not just artifacts, that there really are small objects moving through the coma, and that those objects are not natural fragments. This is the outcome that Avi Loeb is hoping for, the outcome that would force us to reconsider our assumptions about interstellar space, about the prevalence of technology in the galaxy, about our place in the cosmos, and it's the outcome that mainstream scientists consider extremely unlikely, but not absolutely impossible. Which of these outcomes will we see? We don't know yet. We're waiting for the data. We're waiting for the observations to come in, for the analyses to be completed, for the debates to run their course. And in the meantime, all we can do is watch and think and ask questions. Because that's what this moment is about. It's about engaging with the unknown. It's about being part of a scientific investigation as it unfolds in real time. And it's about remembering that, whatever the answer turns out to be, the process of finding it is just as important as the answer itself. And here's the thing. This story is bigger than 3I Atlas. Because 3I Atlas is not the first interstellar object we've detected, and it's not going to be the last. There are others out there, passing through our solar system right now that we just haven't spotted yet. And as our telescopes get better, as our detection methods improve, we're going to see more of them. We're going to study them. We're going to learn from them. and each one is going to add another piece to the puzzle of what interstellar space is like, what other star systems are like, and whether we're alone in the universe. So the investigation of 3I Atlas is not just about this one comet. It's about the beginning of a new era in astronomy, an era where we can study objects from other stars, where we can sample the chemistry and physics of distant systems, and where we can perhaps find evidence that intelligence exists beyond Earth. And that brings us to the final question, the human question. The question that underlies all of this science, all of this debate, all of this fascination. What does this mean for us? What does it say about who we are and what we're looking for? Let's be honest for a moment. This isn't really about a comet, is it? I mean, yes, the science is important. Yes, the data matters. Yes, understanding interstellar objects is a legitimate and valuable field of research. But when you strip away the technical language, the orbital mechanics, the spectroscopy and the image processing, what you're left with is something much simpler. A question that's as old as humanity itself. A question that we've been asking since the first time someone looked up at the night sky and wondered, are we alone? That's the question. That's what's driving this entire conversation, is why people care about 3I Atlas in the first place. It's why Avi Loeb's ideas get so much attention, even from those who disagree with him. It's why these images, ambiguous as they are, spark such intense debate. Because deep down, we're not just looking at a comet, we're looking for answers. Answers to questions we're almost afraid to ask out loud. What if we're not alone? What if there are other civilizations out there building things, exploring, sending their artifacts across the galaxy? And what if one of those artifacts just passed through our solar system, and we almost missed it? That's the fear, isn't it? The fear that we might have already encountered something extraordinary, and we didn't recognize it. The fear that we're too cautious, too skeptical, too locked into our existing models to see what's right in front of us. And on the other side, there's the opposite fear, the fear that we're too eager, that we want so badly to find something that will see it even when it's not there, that will turn every anomaly, every ambiguous data point into evidence of alien intelligence, and in the process we'll lose our credibility, our rigor, our grounding in reality. These are not easy fears to navigate, and they're not just abstract philosophical concerns. They're real tensions that play out every day in the scientific community. When a researcher suggests that an interstellar object might be technological, they're taking a huge risk. They're risking their reputation, their funding, their standing among their peers. Because the burden of proof is enormous. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said. And for most scientists, the evidence we have right now is not extraordinary. It's interesting, yes. It's puzzling, maybe, but it's not definitive. It's not the kind of smoking gun that would force the community to accept a radical new interpretation. And yet, there's a part of us, a part of all of us, I think, that wants someone to ask the question, that wants someone to be bold enough to say, what if? Because even if the answer turns out to be no, even if 3I Atlas is just a comet and nothing more, the act of asking the question keeps us honest. It keeps us from becoming complacent. It reminds us that the universe is vast and strange, and full of possibilities we haven't imagined yet, and it forces us to confront our own assumptions about what's possible and what's not. So where does that leave you and me? We're not scientists. We're not the ones analysing the data, writing the papers, making the discoveries. But we're part of this story too, because science doesn't happen in a vacuum. It happens in a culture, in a society, in a world where people care about the answers. And the more we engage, the more we ask questions, the more we demand transparency and rigour and honesty, the better the science becomes. We hold the institutions accountable. We push the researchers to think harder, to look closer, to consider alternatives they might have dismissed, and we remind everyone involved that this isn't just an academic exercise. This is about something that matters to all of us. You can enjoy the mystery without jumping to conclusions. You can be fascinated by the possibility of alien technology without believing that every anomaly is proof. You can respect the scientific process while still feeling excited by the boldness of researchers like Avi Loeb, who are willing to explore the edges of what we know. And you can do all of that while staying grounded, while demanding evidence, while refusing to accept easy answers just because they're exciting. This is what it means to think critically. It means holding two ideas in your head at the same time. It means saying, I don't know, and being okay with that. It means being comfortable with uncertainty, with ambiguity, with the slow, messy process of science as it works toward the truth, and it means remembering that the truth, whatever it turns out to be, is more important than the story we want to hear. Think about it this way. If 3I Atlas is just a comet, that's still incredible. It's an object from another star system. It's travelled across light years of space. It's carrying information about a place we can never visit, about conditions and chemistry and processes that might be completely different from what we see here. That alone is worth studying. That alone is worth celebrating. And if there's more to the story, if there are real anomalies that point to something beyond natural processes, then we'll find out. We'll find out because scientists will keep observing, keep analysing, keep testing, and when the evidence is strong enough, when it's clear and unambiguous and reproducible, the consensus will shift, the mainstream view will change, and we'll enter a new chapter in our understanding of the universe. But until then, we live in the uncertainty. We live in the space between what we know and what we hope. And that space is not a bad place to be. It's where curiosity lives. It's where wonder lives. It's where the best questions are asked and where the most important discoveries are made. So don't be in a hurry to close the book on 3I Atlas. Don't be too quick to say you know what it is or what it means. Stay curious, stay critical, stay open to the possibility that the universe might surprise you, because it has before, and it will again. And here's my invitation to you. Join me in this investigation, not as passive consumers of headlines, but as active participants in the conversation. Follow the new images as they come in. Read the papers, watch the debates, think about the arguments on both sides, ask your own questions, share your own thoughts, and most importantly, stay engaged. Because this story, the story of 3I Atlas and the interstellar objects that will follow it, is just beginning. And the more of us who pay attention, who care, who demand answers, the better chance we have of finding the truth, whatever that truth turns out to be. So I'll leave you with this. What do you think? Do you believe 3I Atlas is just a natural comet doing what comets do? Or do you think there's something more to the story? Something hiding in those images that we haven't fully understood yet? Drop your thoughts in the comments. Tell me where in the world you're watching from. Tell me what you hope we'll find. And if you want to keep following this investigation with me, as new data comes in and the story unfolds, hit that subscribe button, because this is not the end. This is just the beginning, and together we're going to follow the evidence, wherever it leads. Thank you for staying with me, and I'll see you in the next one.